Hey everybody, it's Mr. Tima here. How you doing? Hope everybody's doing well. Um, Welcome to our section on work. Now, what's interesting about work is it's one of probably the most talked about areas of physics and physical science, but yet we kind of don't talk about it right, or we don't use the right language when we talk about it. So, for example, can anybody tell me some examples when you hear the word work, what that means? Okay. A lot of people will say things like, it could be something like working out, like running. Okay. Horrible writing here, but we're going to go with it. Running, people will actually think about like yard work. Okay. Things like that. People will think about doing homework as work. Sports in general could be work, things like that. And then what causes it? What actually causes work to happen when you do this? Okay. Okay, some people, we just came off of the term forces. So some people say, well, you got to force things to make it work. Okay, maybe maybe that's your parents forcing you to do something, but actually literally pushing something. Okay, moving. A lot of people will think of moving. Some people will say, hey, when I'm working, I'm sweating, I'm moving around, things like that. All right, and then basically something has to change. There better be a change for something to happen. Okay. And this isn't really the definition, but we're going to come back and talk about that, for example, okay, as we move forward. So here is the actual equation for work. Work equals force times distance, okay? And since distance or force is measured in newtons, okay, and distance is measured usually in meters, the unit for work is a newton meter. Okay, so it's newtons per some meter. Okay, here's kind of just like anything we've talked about, work can be positive or it can be negative. And it's kind of just like gravity and friction and all that kind of stuff. So, if we do a quick mathematical calculation, it's actually really simple. It says if a person pushes a block with a force of 50 newtons, 2 meters, how much work is done? Well, what's our equation? F equals excuse me, sorry, wrote that wrong. I have it written right here. W equals force times distance. Okay, so our force is 50. Our distance is 2. What's 50 times 2? Well, that's 100. And then what's our unit? Force is measured in newtons. And then what's our unit for distance? Meters. So it's 100 Newton meters. But what about direction? That's important, okay? So here's where people start getting a little confused about work. So we need to talk about this. We need to think about what are the forces acting on this box? Well, what would be acting down? Some of you are yelling, gravity, gravity. Remember, that's F of G. We'd say that that's the F of G going down, okay? Well, then if we have gravity going down, then we had to have something coming up that's equal and opposite, and we called that something else. And that was the force that is the normal force, F of N. Okay, those are equal. Well, if I'm pushing a box, I'm going to have a little bit of this going back at me, and that's F of F, which is, who remembers? That's friction. Very good. Okay, and then we have this force, which we're going to make it bigger here. Okay, and we're going to say that that's the force of the applied force, or the push force, if you will, but that's the FAP, the force applied. Now, if these are equal, we don't have to worry about the box shooting up or shooting down. We have a little bit of friction and a lot of FAP, or force applied, so we know we're going to have what? What are we going to have in this direction? We're going to have the net force go that way, so we know that we're going to have motion. Okay? Now, in this picture, the way I have it drawn, do you think work is being done? What about work? Do you think work's happening here? Is there any work happening here? Well, the answer is yes. The answer is yes. So we'll give it a little check mark here. And yes, work is happening here. Okay. All right. Let's look at this picture now. All right. Well, let's talk about this. Again, if I have a force applied, and we're going to ignore gravity right now, but let's just pretend that we have the force applied, okay? We're going to have a force coming back of friction, F of F. We've got motion again. We've got motion. I'll just use M this time for motion. Okay, so do we have work? We're going to put a W there. Do we have work? And the answer is yes again. We have work. That's the same picture. Everything's great. But let's try this for example. What if the force applied, here I'll change my, oh I can't, but let's just pretend our force applied was equal. Okay, if our force applied was equal, would the box move? If we don't overcome friction and our force applied happen, would our box move? There would be zero motion here. There would be zero motion. And if we have zero motion, no matter how much effort we put in, is that box going to move? Well, no. We'd say that there's no work then. We'd say there's no work here. Because think about it, if the job that you're getting paid for was to move this box across the floor, you could be sweating, you could be working all day, you could be pushing as hard as you want. Your effort may be happening. Your FAP, your applied force may be happening. But if I came back and the box wasn't moved, am I going to pay you for your work? No, because you didn't do any work. Okay, let's try something different. What about vertical components here? What about vertical components? Okay, so we have the force of gravity pulling down on this weight. Okay, we have F of G's here. F of G's pulling down. Okay. What's going to be going up? Good, yeah, that's going to be our applied force. That's going to be our applied force. And we're going to make sure that our applied force is a little bigger here. So we're going to, F of, that's our FAPs coming up there. Our FAPs are going up. Okay. So is this bar going to move? If the bar is going to move and it's going to go up and we have motion moving upwards, we have motion. So do we have work in that case? And the answer again is yes, we do have work if there's that way. Now, what if I'm just holding this bar? What if I'm just holding it? Like in this picture, this guy's just holding it. So we have F of G down again, but we really have a force applied, but the force applied is equal. Sorry, these should have been much larger so that it's more clear that they are moving up. Sorry, there we go. But maybe our force applied is equal and he's just holding that bar there. Is this weightlifter experiencing energy loss? Is this guy working is he doing energy? Is he expending energy? Yes, he's expending energy. But is he doing work? Technically, no. There's no work here, okay? Because the bar is just standing still. So now you may be thinking to yourself, okay, I got it, Mr. Tima. If you look at these pictures, if we have motion, then we've got work. If we don't have motion, if things are balanced, we have no work. If we have motion, there's work. And if we have no motion, then we have no work. Okay, well that's good. That is a pretty clear example of when there is work and there's no work. The issue is when you get like here. Okay? So now we are saying that this person is moving this direction. Now, I know it's a GIF and it's a little hard to see. Okay, but we're going to all agree that this person is walking in this direction. Okay? Now, let's look at some forces here. Let's look at our backpack. Well, we'd have F of G down on our backpack. Okay, we're going to call we could call this the normal, but we'll just call it the lift force. We're going to say that this is the lift force. The straps are lifting up our backpack. Okay, and kind of the same with the books. Okay, the books have F of G going down, right? And then we're going to say that the books are also being lifted, our F of lift, if you will. I'll just use FL so you don't have to listen to all those clicks. But there you go. There's our lift force. Okay? There's obviously motion moving forward. So now I have to ask you a question. Is there being work done on the books and on the backpack? Is there being work done on the books or backpack? The answer is no. But Mr. Tima, there's motion. There's motion. Why do we not have work then? Well, remember, if you look at this though, if we go back, where was the forces being applied? There was a force being applied to the box and we had motion. So we said we had work. Even on this one, we said, well, there's a force being applied to the box, and if the box is moving, then we did have work. But since the box isn't moving, we don't have work. On here, the force applied was on this bar and we had motion, we had work. When the force was being applied, we had no motion, there's work. Well, now all of a sudden we have motion, but there should be a clear difference in these pictures, especially these guys right here. Anybody pick it up? Well, the difference is the forces, even though there are forces, they are not in the direction of the motion. Okay, so even though we have motion, the forces are not in the direction. Let's pretend this person walks around the hallway. Again, your job is to move these books. You're expending energy. Your muscles are tightening. You're expending energy. That's not the question. The question is, did you do work? Well, let's pretend this person walks all the way around their hallway. Their school is a nice little box like this. And they start over here and they walked all the way around the school. And by the time I come back out to check on them, they're in exactly the same spot. Would I assume that these books in this backpack have moved? I would say no. So that's why there's no work being done. So what is work? Well, work technically is a product of distance and force, which we talked about, in the direction the object moves. That's the important part. So we all get that it's force times distance, but in the direction the object moves. So let's watch this little recap video. Again, it's all our fun people from Eureka. So let's just watch this little video as a recap.
Work. These barbells have a mass of 120 kilograms. Since they are resting on the surface of the planet Earth, we know that the force of gravity acting on them is about 10 times that number of newtons. It takes a very strong man to lift something that weighs so much. Because if the barbell is being pulled down by a force of 1,200 newtons, it must take 1,200 newtons of force to hold it up. Of course, if we were on the moon, where the force of gravity is only 1/6 that of the Earth, anybody can do it. But we're not on the moon. That looks like hard work. But how much work? 1,200 newtons worth? To lift the barbell? How far? Exactly 2 meters. But what if you only lifted the barbell half that distance, say 1 meter? Surely that doesn't take as much work as lifting the barbell 2 meters. When you lift the barbell all the way up, you're doing 1,200 newtons times 2 meters worth of work. When you lift it only halfway up, you're doing half that amount of work. 1,200 newtons times 1 meter. In fact, this is how you measure work in physics. Work equals force times distance. Here you're doing 1,200 Newton meters of work. And here you're doing 2,400 Newton meters of work. That's simple enough. But suppose that after the show, the strong man discovers that his car is stuck in the mud. He pushes it and pushes it, but it won't budge a millimeter. And suppose that at the very same time, the clown, who hasn't got a car, is in the act of picking up the telephone to call a cab. Which of them would you say is doing work at this particular moment? The strong man or the clown? The clown. Because work equals force times distance. And although the telephone receiver only weighs about 2 newtons, while the strong man's car weighs perhaps 15,000 newtons, when he lifts the telephone receiver, The clown is applying a force of 2 newtons through a distance of 50 centimeters, let's say, or half a meter. And therefore, he's doing 2 newtons times half a meter of work, which is 1 newton meter of work. The strong man, on the other hand, may be exerting thousands of newtons of force. But since the car is not moving, there's no distance involved, and the poor man isn't doing any work at all. A force of even thousands of newtons times 0 distance equals 0 work, whereas a force of only 2 newtons through a distance of only half a meter does equal some work, even if it's only 1 newton meter worth. But it's a bit awkward to keep on talking about newton meters of work. So physicists have borrowed the name of a famous British scientist, James Prescott Joule, as the measure of work. 1 joule is the amount of work done when 1 newton of force is applied through a distance of 1 meter. That's to say that 1 newton meter equals 1 joule, which can also be written like this. So the clown did 1 joule of work when he lifted the telephone receiver. And the strong man did 2,400 joules of work when he lifted the barbell. But of course, when he tries to move his car, it's a different story. He does 0 joules of work.
So again, the whole idea is very simple at retrospect. It is you have to do some kind of force over some kind of distance, but in the direction of the motion. It's a little confusing. Make sure you ask questions. Until next time, Mr. Tima, out.